I hope you're all having a great day. I am Mr. Ish. Thank you for joining me for this video. We have to find the volume of this rotational solid. We have y equals root x, we have y equals 1, the two functions which are involved, rotation around the y-axis. What is it exactly that we're looking at? When you're doing y equals root x, you know you're looking at something like that, a radical. When you're doing y equals 1, you know you're looking at something across. But then the area between these curves is this area right over here. If you were to do the intersection of these, root x is equal to 1, then x is equal to 1, you have a point which develops here 1 comma 1, then of course you have this origin 0 comma 0. This rotation is around the y-axis, so you end up seeing something develop on this side. And then you know when you're looking at something over here, you're looking at a solid which will be like this. A complete through and through solid, but it would look like something as you're seeing over here. Like that type of a structure over there is solid. And then we have to determine the volume of this solid. You can do this by two ways. If you again do this representation we have right over here, and you were to draw a Riemann rectangle, look across from your line of rotation or your axis of rotation, which is y-axis, you're looking here along the x dimension. You know the radius here is x, and then circumference is 2 pi x, and then you have a certain height of this rectangle. It's coming from a top of boundary curve and a lower boundary curve. Everything here with respect to function f of x or y, you're doing a top boundary curve which is 1, and then the lower boundary curve which is root x, but you can just write that as this. When you put everything here within the templates of the cylindrical shell technique, you're looking at a volume is equal to 2 pi. And here, since you're looking across in a horizontal x dimension, you're doing your intervals from 0 up to 1. 0 to 1. You have an x over here. This 2 pi x represents your circumference. It will multiply with your height, then you'll have your thickness, which is dx. Your height here is 1 minus x to the 1 over 2. And then dx, you just have to integrate that over that interval, and it'll give you the volume of this rotational solid. You'll have 2 pi 0 to 1 x minus x to the 3 over 2 dx. Integrate this polynomial, it's not hard. You'll have x squared over 2. Here you'll have a x to the 5 over 2 divided by 5 over 2. You have a 2 pi sitting outside from 1 and a 0. You see this with regard to the 1 and the zeros, and this fraction flipping as you bring it up over into the numerator. 5 over 2 becomes 2 over 5. You're really looking at 1 over 2 minus 2 over 5. 1 and a 0, and then you're looking at a 2 pi sitting outside. That's all what it is. When you finish this right here, you have a common denominator of a 10. You have a 2 pi sitting outside. 2 goes in 10 5 times. 5 goes in 10 2 times, but 2 times 2 is a 4. And this is exactly what you get. When you complete this, you'll have 1 over 10 times 2 pi, a 2 pi over 10, but that will simplify to a pi over 5. So the volume of this rotational solid is a pi over 5. And we can confirm this using the traditional disk approach. Now the same question here, this volume question, can be handled using the disk approach. You know, if you have the same representation, if we show you the representation right over here, this right here is the region between the curves, as you're seeing rotation around the y-axis. When you have a rotation around the y-axis, you have to convert everything in regards to x equals format. Here x is equal to y square. You have to convert it into that form, and that equation becomes that. When you're looking across over here, you're hitting this curve right over here. This root x, which is really y square now, x is equal to y square, and that right there represents your radius, because you can draw your discs in this from a lower to an upper dimension or direction, as you would want to see it. And that's exactly what you have. The cumulative sum of these discs which will develop as you do their area, and you accumulate that area over this interval 0 to 1, you get your volume determination. Remember here, radius is the distance from your y-axis to your curve, but the curve here is y square. And then when you look at this disk, it's circular. You have a pi r square, and then the area here with regards to y becomes pi y square square, which is pi y to the 4. And that right there is a cross-sectional area which will integrate over your limit. Volume with respect to y, you have a pi sitting outside 0 to 1. It's 0 to 1 on a vertical dimension and 0 to 1 on the x-axis dimension. Both dimensions, its limits are the same. You have y to the 4 dy. That's it. That right there is all which is going to integrate. You'll have y to the 5 over 5 and the pi sitting outside, and then a 1 and a 0, and you'll end up having pi over 5 as your volume, which confirms this volume right over here. So it's good. Again, you have to look right over here. You're seeing here a disk develop. That disk is exactly what you're seeing over here. The radius of that disk is exactly the distance from your y-axis up to this curve. This curve is root x, but it's also y squared in terms of x. And that question has been solved for you. Volume using the cylindrical shell technique and using the disk method is pi over 5. Remember, for the cylindrical shell technique, we converted something which had a vertical line of axis into a dx type of integral, where you had a circumference component, you had a height component of your Riemann rectangle, and then you had a thickness component, which was your dx. And that is exactly what you had in terms of a lower limit and upper limit. That was a formula we utilized for the cylindrical shell. But the question has been completed. Pi over 5 represents the volume over here. And that's it for this video. Thank you for watching. Have a great day. Bye.